Welcome to everybody's least favorite topic, predicting products of chemical reactions. This is where you're given reactants and you have to figure out what the product is. Let's take a look. We're going to cut to the chase and just take a look at the most important things to keep in mind when predicting products of chemical reactions. And here they are, all four. First thing you got to keep in mind, reactants, which are, remember, they're starting materials, and products, which are the ending substances, must be stable compounds. That is a must. They have to be stable, meaning that if they're ionic, their charges have to cancel. If they are covalent, you have to have the correct number of atoms to make a correct Lewis dot structure. So these gotta be legit stable compounds. You can't just slap things together and call it a day. You have to make sure that they come together in a stable formation. The next thing is you have to know those polyatomic ions, okay, and their charges. They're going to creep up on you from here on out. So you have to know what their names are, what their symbols are, what their charges are, so you can easily just crisscross and you don't have to look things up anymore. Okay, you also have to know those diatomic gases. Remember, Hofbrinkel, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Gotta know that, always remember that they always have a subscript of 2. So hydrogen would be not just H, but H2. Diatomic gases are a must to know, to get in your head. And the last thing is, whenever you're writing out a chemical equation, predicting products, whatever you know from translating, you always have to balance the equation. We are going to start with the simplest kind of chemical reaction, the synthesis reaction. So if you're starting out with just 2 elements on the left-hand side of your reaction, it's going to be a synthesis reaction. Or a combination. You're going to be combining those 2 together. So we have 2 examples down here. We have calcium and sulfur to make calcium sulfide. We also have a little cartoon here with 2 people that are separate, and then they come together and they're now a combination. So in a synthesis reaction, the product will always be 1 compound made up of the elements in the reaction, obviously, and remember, those products must be stable. So here's what I'm talking about. So say we have calcium and let's say nitrogen. Okay, you cannot just say CaN2. That would be wrong, okay, because they're not just combining them together. Sometimes that works. This time it doesn't, okay, because if you remember, calcium has a positive 2 charge, right? Nitrogen has a negative 3 charge. So in order to have the product be stable, you have to crisscross those charges, and what you'll get is Ca3N2. That is the stable compound, not CaN2. Most students just put them together and they get it wrong because they don't crisscross the charges. So you have to remember to crisscross those charges. And, of course, balance the equation. So take a second, balance it, and then see if you get it right. That was easy. Let's take a look at decomposition reactions. You know that it's going to be a decomposition reaction if you're only given 1 compound to start with, and it's not being combined with anything else. Obviously, if it's not being combined with anything, then it's going to have to decompose or fall apart. So it's going to be a decomposition reaction. The products will always be the elements that make up that compound, obviously, because according to the law of conservation of matter, we cannot create or destroy matter. So they're always going to be made up of the elements that compound is made up of. Now, if it's an ionic compound, then you're going to have a metal that's going to be separated out and a non-metal that's going to be separated out. The metal will always have no subscripts. Okay, it'll be by itself. The nonmetals, if they're diatomic gases, you have to remember that these diatomic gases, the Hofbrinkels, will have always automatically a subscript of 2. So you always have to keep that in mind. If they're not a diatomic gas, then you can just assume that they're going to be by itself. We're going to take a look at an example here of a decomposition reaction. So we're going to have lithium oxide decomposing, and we take a look. This is an ionic compound, so we have a metal and nonmetal. Lithium, okay, is the metal, and remember, like we said, metals will always be by themselves. So Li, and then we have plus, and then oxygen. But remember, oxygen is a diatomic gas. So instead of just being O, we have to put O2. Now, you'll look at this and be like, well, it's not balanced. Remember, that's the last step you always have to take, is balancing the equation. So take a second, balance it, and then hit play again and see if you're right. So there is the complete balanced decomposition reaction of lithium oxide. All right, we're going to take a look at replacement reactions next. Our third question is, how do I predict products for replacement reactions? These are going to be a little bit more tricky than synthesis and decomposition. The first thing you have to do is figure out what kind of replacement is it going to be. So remember, a single replacement starts out with a compound and an element, and here's a little cartoon to help you guys remember that. Here we've got an element, that's this lonely guy, okay, and a compound, this mix of this man and woman. And remember, in a single replacement, the compound goes and switches or kicks out one of the elements in the compound. Remember, they have to be the same kind of element. So the guy has to kick out the guy, okay, in the compound, all right, to make this new compound where he's hooked up with the girl, and then we have this other lonely guy. Okay, so that is single replacement. Now, double replacement is where we start out with two couples, okay, or a compound, all right, and they're going to switch partners. Now, remember, they have to always end up as couples, like boy-girl, okay, or if we're talking about compounds, metal-nonmetal. So if we take a look here, the guys, again, will switch places, or the girls will switch places. Either way, we have a new boy-girl combo. Okay, that is a double replacement. So hopefully that picture kind of helps you figure out what kind of replacement it is. Once you know what kind of replacement it is, then you have to figure out who replaces who. Like I said, the metal atoms will always replace other metal atoms, or non-metal atoms will replace non-metal atoms. So you have to kick out the element of the same kind. Okay, so basically in the end, you can't have two metals together, and you cannot have two non-metals together. Because most of these are going to be ionic, you have to have a metal-non-metal combination. Now, lastly, you have to keep in mind, the following when you're writing out the products. Everything that we've talked about before. Making sure that your products are stable compounds, which means that you either crisscross if it's ionic, or you do your Lewis dots if it's covalent. Again, you have to remember those diatomic gases. Always make sure that they have a subscript of 2. If a metal atom is kicked out, remember, he's going to have no subscript, so the metal atoms don't have subscripts if they're by themselves. And then last but not least, you always, always, always balance your equation. Okay, so once you have all these steps down, the last bit of these notes is putting them to practice. So we're going to do some practice problems. So what I want you to do is write down the practice problem, pause, try to do it yourself, and then hit play again and see if you're right. These are our first 3 examples, so go ahead and write them down in your notebooks and hit stop and try to do these yourself. That's the best way to learn, is try to do it yourself and then go ahead and hit play and see if you got them right. Okay, so before we begin the examples though, I'm just going to do a little extra credit shout out. I'm going to tell you the keyword is double replacement. So at the beginning of class, within the first 5 minutes, you need to bring up a little piece of paper that says your name and the word double replacement to get a couple extra credit points. If you forget within the first 5 minutes, then sorry. Alright, so let's get started. This first one is Na plus Cl. So we should first keep in mind that Na is an element, and so is Cl. Okay? It's only a compound if you have two different elements stuck together. Because we have two of the same atom Cl, it's still an element. Okay, so if we have two elements on the reactant side, then obviously, okay, this is going to be a synthesis type reaction or a combination, because we can't have any displacements and they can't be broken apart further into any smaller little substance. So this is obviously a synthesis reaction. A lot of people will be like, oh, synthesis, easy, just put them together. NaCl2. Wrong, okay? You cannot do that. You have to make sure that their charges cancel. So we have to take this step by step. We have to say, all right, sodium is in group 1A down here. He's going to have a positive 1 charge. Chlorine is in group 7A, so he's going to have a negative 1 charge. Okay, and then we have to crisscross or cancel those charges. So a +1 and a -1 add together to be 0. So it cancels out right away. So it's actually just going to be NaCl. Now, in order to balance out the two, you have to balance the equation. So take a minute and balance it already if you haven't done so. Alright, so there's our final equation here. 2Na plus Cl2 reacts to form 2NaCl. Alright, the second one is we're just starting with H2O. So it's not being combined with anything, so obviously it can't be synthesis or replacement. It has to be a decomposition reaction, because we're only starting with a single compound. So we have to break this apart into its elements. So it should be pretty easy. H2O is going to break apart into H, right, and O. However, remember Hofbrinkel. H and O are part of Hofbrinkel, those diatomic gases, so we need the subscripts 2 for both of them. They're diatomic gases, they're always found as little Siamese twins. So it's not going to be just H plus O, it's going to be H2 plus O2. And again, the last thing you have to do is balance the equation. Alright, so there you go. You've got 2H2O decomposes into 2H2 plus O2. So that's the second example. Our last example on this page is K2O plus Br2 reacts to form what? Alright, so again, we always look at what we start with. K2O, this is two different elements that make up a compound. So this is a compound. And then we have Br2, which is a diatomic gas. So this is an element. So we have a compound and an element together, which means that this is going to be a single replacement reaction, because single replacements always start with a compound and an element. So this is single replacement. Now we have to figure out who is going to kick who out. So this element has to kick out either K or O. We have to look at what type of element Br is. Br is over here. He's a nonmetal, so he must kick out or replace the other nonmetal in the compound. So what that means is that Br must replace oxygen. So oxygen is going to be kicked out. Okay, so we can put an O over here. Now remember, oxygen is a diatomic gas, right? So he actually is O2. Right? And when K and Br come together, we have to crisscross their charges. So potassium is in group 1A, so he's going to have a positive 1 charge. And Br is in group 7, so he has a negative 1 charge. So lucky for us, it's just going to be KBr. So those are our two products, oxygen and potassium bromide. Now the last thing we need to do is balance the equation. So take a second, pause, and balance that equation. So there we have it. 2K2O plus 2Br2 reacts to form O2 plus 4KBr. Alright, here's our last example. Al2O3 plus CaNO3 2. So if we take a look here, we've got two different elements in this one making up a compound, and we have three different elements in this one making up a compound. So here we're starting out with two compounds. So if we start with two compounds, it must be a double replacement reaction, right? Because that is the characteristic of double replacement. We start out with two compounds. So when we do this double replacement, we just have to figure out who is going to switch with whom. The easiest way to do it is I always keep my metal atoms the same. Okay, so I'm going to keep Al first, okay, in the compound, and I'm going to keep Ca first in the compound, and then I'm just going to switch the nonmetals. So oxygen is going to switch places with our nitrate group. So when we do that, we have to, so first of all, Al is not going to be hooked up with oxygen anymore. He's going to go with NO3, okay? And Ca is not going to be with NO3, he's going to be with O. Now we can't just write it out like that, because remember, we always have to crisscross charges. These are metal atoms and non-metal atoms, so we have to crisscross the charges. So let's do that. Aluminum. Start with aluminum. Aluminum's in 3A. He's got 3 valence electrons. He's going to lose those 3 to become a positive 3 charge. NO3 is a nitrate group. He has his own special charge, which is -1. Hopefully you have that in your head by now. So when we crisscross these numbers, remember that 3 goes on the outside of the parentheses, what we're going to get is AlNO. Oh, that doesn't really look like an N. Hold on just a second. There we go. So AlNO3, and then we have the 3 on the outside of the parentheses, because we need 3 nitrate groups in order to cancel out the charge on aluminum. Alright, let's do the same thing with calcium and oxygen. Calcium's in group 2, so he's going to have a positive 2 charge. Oxygen is in group 6. He will have a negative 2 charge, because he only needs 2 more electrons to get 8. So a positive 2 and a negative 2 cancel out, okay? If we would have crisscrossed these, we'd have the same numbers, and if they have the same numbers, then we don't need them. So this is just going to be CaO. So our new products are aluminum nitrate and calcium oxide. Now remember, our last step is to always balance the equation. Alright, and there you have it. Al2O3 plus 3CaNO3 reacts to form 2AlNO3 3 plus 3CaO. Alright, so that's the end of these notes. We'll see you tomorrow for some predicting products fun.